Well, welcome to the lesson on weather and climate. Apologize I'm not there, but I wanted to give you this lesson just because it is one of those things that's sort of kind of be difficult to understand, and want to make sure you guys got as much of the sort of effect as possible. And so this lesson is all about weather and climate, and some of the stuff we've talked about in the previous lesson and in the previous class. So some stuff we'll spend some more time on, others will kind of cruise through here. But weather and climate are related to each other, but they are different concepts. Um, so weather is what is going on in the atmosphere at a particular time and place. Um, it could be, think about like when you open your weather app, like what's going on. That's the weather. So it could be sunny, it could be rainy, it could be cloudy, it could be, whatever. And those things are what are called weather. They're just whatever's going on at that moment in time, cold, hot, that kind of stuff. It is oftentimes confused with climate. People oftentimes look at climate change and they look at the weather today and they say, "Oh, it's really cold out, so I don't understand what this whole climate change thing is about." And that's just a misunderstanding of what is climate and what is weather. Just the fact that it's cold outside doesn't mean it's getting colder, and even if it's hot outside, doesn't necessarily mean that it's getting warmer. Oh man, we had rain all week, and it's uh, this we're not in a drought or whatever. And those are different. Those things are what we're looking at and what we're thinking about is climate. Climate will look at long-term trends in weather patterns, and usually these will cover like 30 years at a time. So when we look at like the average high temperature or low temperature for a particular region or rainfall amounts, they're looking at the average for the last 30 years. And that we can look at trends as far as like what is the trend of the climate versus what's going on in a particular day. And the two main factors that determine a climate of a region are temperature and precipitation. We're going to look at those two in the next few slides. First of all, these are our climatic regions. So we kind of got an introduction to this when we looked at the biomes, when we looked at biome projects, because the biomes kind of fall in certain climatic zones. So for example, like a tropical rainforest is going to be in a, tropical, wet climactic zone. Deserts are, arid environments, dry. So these kind of match different biomes as well. Again, so we're going to talk about temperature and precipitation. First, we'll talk about temperature. There are multiple things that affect a region's temperature. So one is, and we're going to go through and look at real live maps just so you can see this on a um, kind of Google Earth type of thing. The first one is altitude. So this is probably the one that kids are most familiar with. If I go up a mountain, it's going to get colder, and so that has to do with how the air pressure works. So as we go up higher in the atmosphere, the air becomes less dense, and therefore it gets colder. So it turns out that it goes down about 6.5 degrees for every kilometer you go up. So if I go up, you know, a mile, if I go 5,000 feet up a mountain, I can expect it to be, you know, you know, 20 degrees colder. So that's how that works. And for me, living out west, or being from out west, when you escaped the summer heat to go up to the mountains because it was colder. One example here is Mount Kilimanjaro. Kilimanjaro has glaciers on it, even though it is right at the equator. And so that's one of those examples here. And I want to show you this. So if I can escape this slide here and show you this on um, Zoom Earth here. And so what we want to show here, the first one being altitude. So if we can zoom in here and look at a place like Colorado. So this is a live look at the temperature readings. Satellite technology can use basically infrared cameras to pick up the surface temperatures of the Earth at any point on Earth, which is pretty cool. So when we look at the lower lands east of the Rocky Mountains, you can see it's cold, right? It's 26 degrees over here. And if you go over here, it becomes even more mild. But if you go into the mountains in the Rocky Mountains, you can see how the temperature quickly decreases to where, I mean, it's 6 or 7 degrees, 5 degrees just west of Fort Collins. But if you go into Fort Collins, you'll see it is 20 degrees warmer. And that has to do with the altitude. The mountains in the Rocky Mountains are, a lot of them are over 10,000 feet, 12,000 feet. So you're going to see, whereas like Fort Collins is about 5,000 feet. So a huge difference in altitude and how much colder it is. So the next one here is latitude. This one is another one that is fairly obvious. The further that I get from the equator, obviously it's going to get colder. We're going to do an activity next class on Friday or on Thursday and Friday, depending on what class you have. That's going to prove this. But in general, locations closer to the equator are going to be warmer than locations that are closer to the poles. Um, and so we can, I don't need to look at a map to show you that, but we know that it's warmer at the equator than it is at the poles. Now, the next two here are ones that are maybe a little bit less known. And so the first one here is ocean currents. The movement of the oceans has a huge impact on a region's climate. And there is, lots of examples to look at from here, but you can look at so here on this map, you have these ocean currents here in the Atlantic Ocean and the Pacific Ocean. And if you notice on the East Coast, the water that is off the East Coast is coming from the equator. It's called the Gulf Stream, and that water comes from the equator, goes up, and then goes up north towards England or Great Britain. And so the water off the coast on the East Coast is warm. The water came from the equator. Now, on the flip side, if you look on the West Coast of the United States, the water there comes from the North Pacific. And so the water comes from a colder region. So the water off the West Coast is cold. And if you've ever been, which I've been in both oceans on the East Coast and the West Coast is significantly colder waters. And therefore, the people that live over there experience cooler climates. For example, San Francisco is like 50, it doesn't even reach 60 degrees on most days, just because the water there off the coast is always like in the 50s. So it's always cold in San Francisco. Whereas on the East Coast, the temperatures are pretty mild, even in the wintertime if you're along the ocean there. So just to show you that, again, we're going to go to our map. So a couple things I want to show you is looking, whoa, went too far, way too far. So one of them is to look at the ocean currents that are off of the coast of California. So these waters come from the north and they're coming south from up here. And so we can see in a place like San Francisco, because the ocean temperatures here are very cold, relatively cold, you can see that San Francisco, I mean, it's only 53 degrees in San Francisco, and all along this coastline, it's relatively cold. Even in Southern California, where it is, relatively warm during the day, I mean, you can see here how it's only in the 50 degrees range. But if we flip the side over here on the East Coast, it's going slow because I got a lot of stuff going on right now. But notice over here, if we at same latitude, I mean, we're just going over on the East Coast, same latitude, same, solar radiation from the sun. We can see how here, because the water comes from the equator, how much warmer the water is. I mean, same latitude over here, and you look at places like South Carolina or Georgia, where we're getting really much warmer temperatures, even all the way up here into North Carolina, you're getting pretty mild temperatures. But you can see the ocean temperatures. And if we zoom out just a little bit and follow the Gulf Stream up, we can look at how this Gulf Stream pushes this warm water all the way up into the Great Britain area. So here's the Gulf Stream, and you can see this warm water just goes all the way up in here. And so this is a good analogy here as well. As you look at London, London's relatively cool. It's 44 degrees. It's not exactly a warm day, but London, it has the same latitude as Winnipeg, Canada. So here's Winnipeg, Canada, way over here. And notice the difference. Hey, it is 17 degrees in Winnipeg and 44 in London. So the reason for the 30-degree difference in air temperature is the fact that London and all of Great Britain here sit in this Gulf Stream that's pushing warm water into the area, and then making the climate warmer in these regions. I mean, even Reykjavik in Iceland, it's 38 degrees, but way down here, I mean, this is in the Arctic Circle. And down here in Winnipeg, it's 17 degrees. So just a huge difference that this Gulf Stream makes, that the water coming from the equator as opposed to, on the West Coast where the water is coming from further north. So all these places are very cold, much colder. I mean, 11 degrees, geez. -4. Bone chilling cold way up here. And then, so the last one has to do with how close you are to a body of water. And this kind of goes along with the previous one, and that why San Francisco is so cold, and places like, Charleston, South Carolina, or, you know, parts of Georgia, Savannah, Georgia, are warmer. Because the water is cold off the coast of San Francisco is cold. And that's just the way, because that water, air coming off the ocean there is cold, and it keeps San Francisco relatively cold. Whereas on the East Coast, the water off the coast there is warm. I mean, you saw the water temperatures were, over 70 degrees still. So it's going to keep the coastal areas on the East Coast relatively warm comparatively to the West Coast. And that's just because you're so close to those oceans, which are influence the climate. Another example is, like, I go to San Diego. I used to, and I lived in Arizona, I used to go to San Diego all the time. And you would drive through the desert in Phoenix, and there was a time we were driving, it was 122 degrees in Southern California, and in the deserts of Southern California. And as soon as you went over the mountains and then into the San Diego area, it was 65 degrees. It was 65 in San Diego, and only just a couple hours east in the desert, it was 122. So that is just shows you the influence that the ocean has on San Diego's climate. The next thing, you guys will watch a convection current. You guys have watched a convection current video. So the next thing I want to move to is precipitation. And this one we didn't want to start from the beginning. The next thing we were going to look at is precipitation. Now, this one we're not going to spend too much time on because we already talked about it in the last class. But I told you there are two ways that we get precipitation, and that is here in Indiana, we get it with cold fronts, which are driven from the prevailing winds. On the West Coast, a lot of their precipitation is drawn from the presence of mountains. And so this is how a place like Indiana gets their rain. So we live up here where the westerlies are. So the storm systems will push from west to east across the United States. And as it pushes across the United States, I told you guys, you get forced uplift. Those cold fronts come in, you get forced uplift, and you get rainfall. And that's how prevailing winds will generally move cold fronts, through areas, and that's how you get precipitation in those areas. The other one is with mountain ranges, and this is what I was explaining in class last time. And that's how on the windward side, where the wind is drawn and driven up, that forced air that has to rise cools, condenses, and can form rain on the windward side. And then as the air column then travels over the mountain onto the leeward side, the air is now sinking, and sinking air actually prevents rainfall from happening. And so you get a desert on the other side. And we saw that in the maps of the West Coast, how everything on the west side was wet and on the east side was a desert. The last thing to talk about here are microclimates. And this is one where you have to really kind of zoom into the map. So microclimates are areas where the climate is different in a small area compared to the surrounding areas. And a perfect example of this are major cities. Because of all the concrete and asphalt, those things retain heat throughout the day, and at night they re-radiate the heat up, keeping the city warmer at night than the surrounding areas, and oftentimes leading to warmer temperatures during the day than the surrounding areas. And so those are what are called microclimates. It's also called the urban heat island effect. And those things, there's also things where cities, because of the pollution, also can create more condensation and rainfall. And so you actually get more rainfall in some of these cities um, compared to the surrounding areas. Now, I want to get out of here because that's the last slide, but I want to show you this on the map. And there is no, the perfect example of a microclimate is where I'm from, which is Phoenix. Let's see if how accurate this is. Sorry. See if we can really get in here, the Phoenix area. Yeah. So what we want to look at, this is the Phoenix area, and so tons of city, tons of concrete, tons of asphalt, and so you'll notice that the inner city here is in the upper 50s, so 58, 59 degrees. But if you just go just outside of town a little bit, and I'm talking just, I mean, notice it's not a huge difference, but a few degrees makes a big difference because if this is the summertime, and it's 120 degrees in Phoenix, just getting out and it being 110 degrees is a big difference, especially at nighttime in the summer. Whereas a lot of times in Phoenix, it might not even get below like 95 degrees. But if you go to the outside of town, you can usually feel it get into like the 80s. So notice the difference here. I mean, this is the same elevation, same latitude, just a little bit over, and you're seeing almost a 10-degree difference in the temperature just by, being in a rural area. I mean, right here, 10 degree, it's almost 10 degrees difference. Same thing if you get out here. These are all cooler regions down. Let's go down south here to get out of the city a little bit. And you can see that even down here, I mean, looking over here, it's 40, it is 10 degrees difference. And if you just get outside of the city a little bit. So that's a micro climate where the city itself, because of all the infrastructure, actually makes it warm. So, anyways, let's see. There was one more thing I wanted to show you here, and that was let me get out of here and to here. This was an image that I wanted just to show you here because one thing you need to know are these cells. And so, let's see if it'll let me zoom in. There you go. So, Hadley cells. So, these cells, you don't need to know the names of these cells particularly. You just need to know that they're there and what they do. There's a Hadley cell and a Ferrel cell, but basically because the equator is getting the most amount of sunlight and the most amount of heat, what we know about air is hot air rises. So at the equator here, you're getting rising air coming from the equator. And the way these convection currents work is as the air rises, it reaches a ceiling, and it's usually the troposphere. So the troposphere acts like the stratosphere acts like a ceiling for the air columns. And so as it moves up, it hits a ceiling we call the stratosphere, and it can't go anywhere but, left or right or north or south in this case. So some of the air goes north, some of the air goes south. As it's up there, that air column begins to cool because it's really high up and it's cold up there. And as the air column cools, it, for some reason, sinks at 30 degrees north and 30 degrees south. And if you remember what we talked about with that rain shadow thing, sinking air actually prevents rainfall, whereas rising air is favorable for rainfall, which is why all this region here is where all the tropical rainforests are. Not tons of rain here. You look at 30 degrees north and 30 degrees south, and that is where all of our deserts are. The Sonoran Desert in Arizona, the Sahara Desert in Africa, the deserts of Australia all happen to be right around 30 degrees north and south. And that's because that is where the Hadley cell on both sides here are coming back around and sinking. That air then goes to the surface, and some of the air will go back to the equator, while some of the air will continue going north into this ferrocell. And you get the same thing happening here. Again, at 60 degrees north, you get uplift again. And this is why the areas of boreal forest in Canada and Siberia are all lots of snow, lots of precipitation, lots of forests. And that's because you have rising air again. And then this continues around until it gets to the poles. You do have a polar cell up here where you do have sinking air at the poles. And that's why our tundras are extremely dry because you have that sinking air here. But this is what those cells do. There are more videos and information in your textbook about how these things work, but you just need to know that they're there at the equator of rising air. That's why you get rainfall. The air columns then sink at 30 degrees north and south, and that's where we get all our deserts from. You don't need to know that that's the Hadley cell or the ferrocell, but you do need to know what is going on at these locations. So hopefully that was helpful. Sorry I'm not there. It's way better than when I'm there. So anyway, let me know if you have any questions.